Okay. The endpoint of the titration is defined as where the color changes from colorless to pink. That's the endpoint. That's where the indicator indicates that the reaction's over. Where the indicator indicates where the reaction's over sometimes isn't exactly where the reaction is over. In this case, it overshoots the reaction just slightly. But the amount that it's overshot is negligible. It doesn't really lead to any significant error. But when we overshoot it like this, it was significantly overshot. So let's say rather than getting it from colorless to pink within a half a drop, you got it within like a half a milliliter. The color is going to maybe darken a little bit, but once it gets to a certain shade of pink, it's hard to tell how much you overshot it by. You could have overshot it by half a milliliter or 10 milliliters and it looks the same. But anyway, if we overshoot that, then we've added way too much sodium hydroxide titrant. If we add way too much sodium hydroxide, way more than was required to neutralize our HCl, then what's that going to do to the molarity of the sodium hydroxide? So, yeah, it's going to be a lot lower, the concentration. So we just circle it out here. What did you guys get for number 2? Lower? So a drop of base was left adhering to the tip of the base burette. So if a drop of base, that means we added extra base that we didn't have to. And so a little bit extra base in there. That wasn't necessary to neutralize. It's the same thing. It's overshot. We overshot the titration. Yeah. So that's correct. How about number 3? What did you get for number 3? Higher. Some drops of acid were left clinging to the walls of the flap. Yeah, that means that what happens is you get splattered. And sometimes this saves you. I've had titrations where I overshot it and it came out a little bit too dark, the pink color, and I wasn't sure if I hit it right. But I was saved. I was saved because once I rinsed all the splatter in, then it went back to colorless. So that was enough acid to revert back to colorless. And so sometimes I use that as a little reserve, so in case I do overshoot, because sometimes you run out of patience and you just want to get it done as quickly as possible. But if you don't wash those acid drops in, then you haven't added enough base. And so that's correct. If you haven't added enough base to neutralize all the acid, then you're going to think that the sodium hydroxide is more concentrated than it really is. And so higher is correct. How about number 4? What did you get for number 4?
Higher.
You obtained standard acid solution in a wet beaker. So if you obtained it in a wet beaker, then that means that you think you have this concentration, but the concentration you're going to have is actually going to be, the true concentration will actually be lower or higher than the standard. It'll be lower, the true concentration. And therefore, if it's lower than the true concentration, then you're going to add less sodium hydroxide to neutralize it. If you add less sodium hydroxide to neutralize it, then it's going to appear higher. That's correct. 5. Use the wet flask for titration. What did you put for this one?
I put it higher.
Higher?
But I think it might have no effect.
Or no effect? It might have no effect? Higher or no effect? You put no effect on?
I put no.
No effect. Anybody else? Yeah, no effect. This is why we can wash, we wash the half droplet in there. It has no effect in the Chem 1A titration because in the Chem 1A titration, we're interested in how many moles of acid, how many moles of base we have in here. In the Chem 1B titration, we're monitoring the pH, and the pH is dependent on the concentration. So if you add in a whole bunch of water there, it changes the pH. And so in Chem 1B, we try to minimize how much water we put in there. Otherwise, the pH starts to go up. But here, it's actually no effect. That's why we don't bother drying the flask. As long as it's DI water, it should be all right. 6, you added 4 drops instead of 2 drops of phenolphthalein. What do you guys put for this one?
I said no effect.
No effect. No effect.
No effect.
No effect. Well, there actually, what impact will that have? If you add 4 drops instead of 2 drops of phenolphthalein, phenolphthalein is an acid. It's a weak acid. It's this, HP. I'm just going to write phenolphthalein pH. This is the anion. It's organic. It forms phenolphthalate. But anyway, this is colorless. And what happens is, if we have some sodium hydroxide, which we're adding as a titrant, that reacts with the phenolphthalein, and it converts phenolphthalein from the colorless form to the colored form. This is just a double replacement reaction. So we're going to form sodium phthalate, or phenolphthalate, sodium pH, and H2O liquid. This sodium salt is pink, or red, or whatever you want to call it, purple. That's the pink color. And so if we add 4 drops instead of 2 drops, then in order to convert this from colorless to pink, we're going to have to add more base. If we have to add more base, then that's like overshooting it. Because we're adding more base, not for the acid, but for the extra phenolphthalein in there. And so if we add more base, then it's going to be lower. Okay. It's not a very strong acid, and it's not very concentrated. If we're really concentrated, then yeah. But this is why you want to be consistent. This is systematic error. Yeah, we're going to add 2 drops. It's going to lead to a little error. That's I prefer 1 drop actually, phenolphthalein in titrations. All right, so you need to have that done. And that's basically it. Okay, so turn this in. You do that. Okay, other questions? Okay, let's continue then. Where we left off, I So I inputted some more scores this morning.
I noticed the one for Charles Law, that one has it not graded yet. Like it shows that the points are there, but it's like not affecting. So I was just wondering.
Did you turn that in with everybody else's? I didn't see it. I'll take a little look for it. If it's blank, it's because I'm missing it.
Yeah.
So, All right, let's take a look at intermolecular forces. See what types of questions you could potentially be asked for this. What were the three types of intermolecular forces that we discussed so far?
Dipole forces,
Dipole,
instantaneous dipole,
instantaneous dipole,
hydrogen bonds.
and hydrogen bonds. Instantaneous dipole goes by other names as well. You know the other names for instantaneous dipole?
Induced.
Induced dipole and one other name.
London forces.
London forces. All right. Well, let's just look at intermolecular forces in general here. Questions here. Why are intermolecular attractions stronger in the liquid state than in the gaseous state? Well, this question depends on if the liquid and the gas are at the same temperature. If the liquid and the gas are at the same temperature, then what we have is the liquid is sticking together, and the gases are not gaseous. It doesn't mean that they can't stick to one another. So if they're at the same temperature, then we expect the solids to have the strongest force binding them together, and then liquids, and then gases. If they're at the same temperature, but if they're at different temperatures, then it's hard to compare. Because if we look at a solids, the intermolecular force, IMFs, are much stronger than the kinetic energy. In liquids, the IMFs are approximately equal to the kinetic energy. And in gases, the IMFs are less than the kinetic energy. The kinetic energy can break them apart. And so we have to add the qualifier here at the same temperature. How do intermolecular attractive forces influence the boiling point of a pure substance? The stronger the intermolecular forces, the harder it is to vaporize, to evaporate. Therefore, it will impact the boiling point. The higher boiling points are going to be for stronger forces. The lower boiling points are going to be for weaker forces. Why does the molar heat of vaporization depend on the strength? Molar heat is how much energy it takes to vaporize a mole of liquid. That's going to depend on how sticky the molecules are. A tall glass cylinder is filled to a depth of 1 meter with water. Another tall glass cylinder is filled to the same depth with syrup. Identical ball bearings are dropped into each tube at the same instant. In which tube will the ball bearings reach the bottom first? The water. Explain your prediction in terms of viscosity. Viscosity is resistance to flow, and so the syrup is viscous, high viscosity. The water is going to be lower viscosity. So, and intermolecular attractive forces. The syrup is going to have strong intermolecular attractive forces, much stickier than the liquid water.
Is viscosity directly related to IMF?
Mm-hmm. Yeah, there's a simulation, if you want to see it, a molecular dynamics simulation. dynamic simulation of viscosities. Let's see if it comes up. These are more general discussions. The molecular dynamics simulation, I'd have to look at. It's not popping up, but it'd be something like this. You know, the more sticky. These are all IMFs here, the purple, intermolecular forces. These IMFs here are hydrogen bonding interactions. These are all hydrogen bonding. And so the more sticky these are, the less things are going to flow through it as well, like ball bearings, because you have to break apart all the water molecules in order to make room for the ball bearings. And the stronger the INFs, the more difficult it's going to be to flow. So if water spills on the laboratory desktop, it usually spreads over the surface, wetting any papers or books in its path. If mercury spills, it neither spreads nor makes paper wet, but forms little drops that are easy to combine into pools by pushing them together. So just an explanation for these facts in terms of apparent surface tension and intermolecular attractive forces of mercury and water. Normally, this is explained using cohesive and adhesive forces. And so cohesion or cohesive forces are intermolecular forces of attraction between like particles, versus adhesive forces would be attractions between unlike. And so adhesive forces would be like glass. If we have glass, clean glass, if it's dirty glass, water tends to bead. But if it's clean glass, water likes glass, and so it spreads out and wets the surface. Glass is polar, water is polar. However, mercury is nonpolar, and glass is polar. So if we have mercury, mercury beads the surface here. And so what we have here is mercury would much rather be with other mercury atoms than with glass, whereas water would prefer to be with glass than with other water molecules. And so when something beads, then we say that the cohesive forces are stronger than the adhesive forces. And this has to do all with intermolecular attraction. When something wets the surface, then the cohesive forces are weaker than the adhesive forces. And so this gives us differences in the meniscus. Mercury much prefers to be with itself and with glass, so it tries to minimize contact with glass. And so this would be Hg liquid. Hg liquid minimizes contact until it has to here. Gravity pushing it down. Versus water, this is the glass tube. Water maximizes its contact. And so water tries to climb up the inside walls of the tube until gravity pushes it down. If it's a very thin tube, thin tubes we call capillaries, and then it can climb quite high because of the adhesive forces there. And it's just a water glass attraction. All right, there's some more of the dust. All right, let's look at the types of intermolecular forces here. 25. Other things being equal, which produces stronger intermolecular attractions? Induced dipole forces or dipole forces? Which one would you expect to have stronger attractions? Dipole. That's correct. Dipole are permanent on time average. And so all things being equal, you expect it to be stronger. In fact, all things being equal, we expect induced to be the weakest, followed by dipole, followed by, which would be the strongest? Hydrogen bonds. But induced dipole can be significant. In fact, induced dipole can be quite strong under certain conditions. And the certain conditions are if you have a lot of electrons. If you have a lot of electrons, then what we can have is a pretty big instantaneous dipole. And so the more electrons there are in the atom or particle, the larger the induced dipoles, instantaneous induced dipoles. Well, anyway, this is, in 2002, a team of scientists discovered that induced dipole forces among millions of tiny hairs on gecko feet and the surface are what allow these lizards to adhere to walls and ceilings. So that means the induced dipole in the hairs on the gecko feet are significant. And if you hold the weight of this to a ceiling or a wall, it's got to be strong. And so under certain conditions, induced dipole are quite strong. What are the principal intermolecular forces in each of the following compounds? When we do this, we have to determine, is it polar or nonpolar? If it's polar, does it have just a dipole or is it hydrogen bonding? And so if we look at the first molecule there, what we do is we just draw the Lewis structure for that, and then C. And so NHCH3 2. It looks like we have a nitrogen with three things bonded to it. We have a hydrogen here, and then we have a methyl group here. I'm not going to expand this. I'm just going to keep this written as a CH3 and another methyl group over here. So we have two methyl groups and a hydrogen. Are we missing anything? Now, is this trigonal planar? The shape of this. It's trigonal pyramidal. What's causing these three to go down and form a pyramid? A lone pair. So we're missing a lone pair here. If there's no lone pair there, it'd be trigonal planar. It also have a positive charge, but there's a lone pair. So is this polar or nonpolar? It's polar. And, here's the primary place, nitrogen and hydrogen. And when we look at nitrogen and hydrogen, that's special. When nitrogen is bonded to hydrogen, or when oxygen is bonded to hydrogen, or when fluorine is bonded to hydrogen, then it's an unusually large dipole. And so this is going to be an unusually large dipole. And this is H bonds. And so this can hydrogen bond to another dimethyl. We call this dimethylamine. And so can hydrogen bond to another dimethylamine. I saw something kind of interesting. in C&D News recently. A lot of amines are in drugs, like codeine is an amine, heroin is an amine. A lot of amines are drugs. But, what is it? Let's search it. What is that? You know, water, when we look at water, water has kind of a structure to it, even though this is what we call kind of amorphous, but there is some structure because of the way things are oriented. They orient like this to try to maximize the hydrogen bonding interaction. But did you know, like under high pressures, the kind of the structure of this, which is changing all the time, is different than at lower pressures. And so at very high pressures, things can get compressed a little bit more, and so these hydrogen bonding interactions aren't as optimized as they are here, even though this looks all random. There is some structure to this. Let's see if I got this article here. Yeah, this is it. So we're talking about hydrogen bonding and this kind of stuff. Let's take a look at this article here. It comes out. It's very slow. I don't know why. How a chemical protects fish from the extreme pressure of the deep. Trimethylamine N oxide fortifies hydrogen bonds in water. In the freezing dark depths of the ocean, organisms face pressures over 1,000 times as great as at the water's surface. Now scientists have discovered one clue to how deep sea organisms survive these high pressures. The chemical trimethylamine N oxide. Trimethylamine N oxide is pretty simple, but rather than having that lone pair there, we're going to have this oxygen like this. They're probably going to draw a double bond here, but we can't because we can't expand the octet. So it's kind of a funny chemical. This is going to give a positive formal charge on the nitrogen, negative formal charge. So it's tetrahedral like this. But this is trimethylamine N oxide, TMAO. Found in the tissues of many marine organisms. So they found this in the tissue. Amines have a certain smell to them too. It's ammonia kind of smell. And so a lot of people can smell the fish and tell, is it fresh or what, depending on what's happening in the fish. Stabilizes the structure of water. 8 years ago, scientists observed that the deeper in the ocean a fish lives, the higher the concentration of TMAO in its tissues. TMAO is known to stabilize proteins in marine organisms by counteracting the propensity for high pressure to force water inside proteins and denature them. But how was a mystery. So you can read through this if you're interested. But basically, it stabilizes this here. And then this is all dynamics, so we'll throw in some TMAO in this. These are all quantum mechanical calculations, and then see how that changes things. And then they can increase the pressure, make things more dense, lower the temperatures, etc. Okay, so this TMAO, well, TMAO hydrogen bond. Yeah, actually, no. TMA won't hydrogen bond because TMAO stands for trimethyl. I only have dimethyl here, so this would be DMAO, not TMAO. So I need to change that. Here, let me correct this. Now, does this hydrogen bond? No, because these hydrogens are not bonded to the nitrogen. These hydrogens are bonded to carbon. And those are non-polar. It's like oil. And so this does not hydrogen bond. And so if that's the case, water prefers to be with water because water can hydrogen bond with other water molecules. But it turns out that you're not learning all of the intermolecular forces. There are others. There's ones that are called ion dipole. Ion dipole interactions are even stronger than hydrogen bonding interactions, potentially. And so even though this doesn't hydrogen bond, this can ion dipole. That is, I told you that H bonds consist of unusually large dipoles. Well, this is a much larger dipole because this is full charge. Delta means a partial charge. This is a full positive, that's a full negative, which is even higher, and which would be a bigger dipole. So ion dipoles are greater, but ion dipoles aren't discussed in our book, so I'm talking about them. Maybe they're discussed in the next chapter, solutions, so we'll get there. Okay, let's look at the next molecule, CH2F2. So CH2F2. Okay, can you draw the Lewis structure for this quickly? What would it look like? Does this hydrogen bond? Well, usually we just draw the Lewis structure. Yeah, it looks like a hydrogen bond. But what would it look like? Yeah. Two fluorines. Okay, what's the shape around carbon? Tetrahedral. So we'll throw in the two fluorines here and the two hydrogens here. It doesn't matter where I put the hydrogens and where I put the fluorines. They're always going to be side by side. So if I put the hydrogen over here and the fluorine over here, they're still side by side. This is 109. And looking from behind, it's still 109. And so when I look at this, is it polar? Yeah, which way is the molecular dipole pointing? The molecular dipole is going to be pointing this way. So that would be the molecular dipole. Can a hydrogen bond? Yeah, no, this can't hydrogen bond. This can't hydrogen bond because the hydrogens are bonded to carbon, not fluorine. If they were bonded to fluorine, yes. And since they aren't, then it's not an unusually large dipole. This is just this is a big dipole. Not a moderate sized dipole. It's quite polar, but not as polar as having
Are hydrogen bonds only for fluorine, oxygen, and nitrogen?
Yes, the three most electronegative elements on the periodic table. And that's going to create the biggest dipole with hydrogen. And so this would just be dipole. That would be the principle. All of these, though, have London. Anything with electrons has London because electrons are moving. And what can happen is this dipole can grow bigger or it can grow smaller depending on how the electrons migrate. So for example, if the electrons decide to all migrate and stick right on fluorine here and right on this fluorine, then this dipole can grow bigger. Like this. However, if the electrons kind of hover around carbon, say, they start moving, they move back towards carbon, and let's say they're hovering around carbon more than they normal, then this dipole can grow smaller. And so when we have instantaneous dipoles, those instantaneous dipoles are constantly forming and disappearing. And what's happening here is that what it does is it grows bigger and smaller and whatever. This is the average. The black is time average. So the dipole fluctuates depending on where the electrons are. And those fluctuations lead to a net attractive force. And so what we're going to have is we're going to have both a permanent dipole, this black, the time average, plus these fluctuations. In other words, dipole and dispersion, or dipole and London forces. Dispersion or London forces, which are instantaneous dipoles. And so anything with electrons will have instantaneous dipole, induced dipole, dispersion, London, all the same thing. Same thing here. Dipoles can grow up and down depending on how the electron, it's called polarized, depending on how the electrons polarize. Look at C3H8 next. C3H8 is propane. I'm going to draw 3 carbons, so just draw a zigzag chain of carbons like that. And then fill everything else with hydrogen. So this carbon needs 3 more bonds. This carbon here needs 2 more bonds. And this carbon here needs 3 more bonds. This is not a wedge dash 3D drawing of this. This is just a Lewis structure. But this would be C3H6 plus 2 is 8. Each 8. Propane. Does propane hydrogen bond? No. What we have here is when we have carbon and hydrogen, that's an unusually small dipole. It's an unusually small dipole, and it's so small we call it nonpolar. And so this is nonpolar. Even though it's nonpolar, in one instant of time, it could get polarized. That is, if right now the electrons are spread out evenly, but if the electrons weren't spread out evenly, let's say it creates just a temporary dipole here. Let's say it goes like this. Normally over time it's spread out evenly. But even here, let's say it becomes skewed. If it becomes skewed, then we set up a dipole. That dipole is not going to be permanent, because it's not stable. But what we're going to have is we're going to have instantaneous dipole that can attract one another, and therefore London forces are present here. Called London.
So if it asks what intermolecular forces are present and it gives us a compound, or London, instantaneous, are they always? Is that always the answer?
There's always, this one's asking what's the primary. So all 3 of these have London, but the first one could hydrogen bond, so that's more significant. The second one has, dipole in London, and the third one's just London alone.
So it's always going to be a secondary. It's always going to be there.
It's always going to be there, and if there's no dipole, if there's no permanent dipole or hydrogen bonding, then it's the only force that's present. And so something like in propane, there's nothing else, only London.
I'm guessing that applies for all of the, I forgot what they called the CHs.
Hydrocarbons?
Yeah, all the hydrocarbons.
Yeah. That's the same for all hydrocarbons. Compare dipole forces and hydrogen bonds. How are they different? Well, hydrogen bonds are big dipoles, and dipoles are just normal-sized dipoles, whatever those are. And how are they similar? They're both dipoles, and they're just different size dipoles. On the basis of molecular size, molecular polarity, and hydrogen bonding, okay, the bigger the molecule, the more electrons it has. So for example, propane is a gas. You can liquefy it, like in barbecue tanks, with a little pressure and liquefy it. You know what butane is? Yeah, maybe a liquid, almost a gas. Do you know what pentane is? A liquid. Pentane is 5 carbons. Hexane is a liquid. Eventually, you get bigger and bigger hydrocarbons, and they turn into solids. And we know that gases are going to have weaker forces, liquids have stronger, and solids have the strongest force. So when the molecules grow bigger, these instantaneous dipoles can get quite big. It's not gravity that holds them; it's the instantaneous dipoles that hold them.
So does it have to do with like how many carbons there are? The more carbons.
The more carbons, right, the larger the instantaneous. But the more electrons, it can go. It doesn't have any carbons, just whatever. All right, which one has a higher boiling point? Well, which one has a higher boiling point? The higher boiling point is going to be the one with stronger intermolecular forces, the one that's going to be more sticky. So methane versus ammonia.
Ammonia.
Ammonia has
Hydrogen.
hydrogen bonding. Sure, that's going to. Methane's only London. Methane versus carbon tetrachloride. Both of these are tetrahedral. Both of these are non-polar. So both of these only have London forces or dispersion or instantaneous dipole, whatever you want to call it. Which one's going to have a higher boiling point?
Tetrachloride, because it's bigger.
Yeah, carbon tetrachloride because it has more electrons. Hydrogen only has 1. Chlorine has a lot more electrons. And the more electrons you have, the more the electron cloud can get polarized. So, like fluorine versus hydrogen. And so, some people will say it's heavier. Yes, it's heavier, but still, a molecule weighs next to nothing. And so it should be easily vaporized. So what's holding them together are stronger dispersion forces. Carbon tetrachloride is a liquid. Methane is a gas at room temperature. So the forces are significantly stronger in carbon tetrachloride. Argon versus neon. Which one has a higher boiling point?
Argon.
Argon has more electrons. Neon only has 10. Argon is 18. H2S versus pH3. H2S versus pH3, both of them are polar. And so if both of them are polar, it's going to depend on which one has a bigger dipole. The shapes are different though, so it's a tough comparison because when you look at the shape of H2S, it's like water, or it should be like water. Tetrahedral, EP, electron geometry, and bent molecular geometry. pH3 is like ammonia, trigonal, pyramidal. So which of these will have a bigger dipole? Which one's more electronegative, sulfur or phosphorus? Sulfur is more electronegative. And so sulfur should have a bigger dipole. So both of these have dipole. H2S should have a bigger dipole, and therefore the higher boiling point. They're both around the same number of electrons. If you look at sulfur has 16 electrons, phosphorus has 15 electrons. But we have 2 hydrogens here with 1 electron each, so that's 16. I'm talking about total electrons now, not just valence electrons. They have this, when we're doing the polarity, we're looking at the total. So 16 plus 2 is 18 electrons. This is 15 plus 3 is 18 electrons total. Valence and core. What feature of the hydrogen atom when bonded to an appropriate second element is largely responsible for the strength of the hydrogen bonding between molecules? Sulfur and phosphorus won't hydrogen bond. They won't hydrogen bond because they don't have the electronegativity to pull the electron cloud too far away. So electron cloud can be polarized, but hydrogen puts up a significant fight for that. So sulfur is more electronegative. Same thing here, phosphorus is more electronegative, so it pulls the electron cloud more than hydrogen, but hydrogen doesn't give up here. Whereas if we had something like ammonia, let's look at nitrogen and hydrogen here. Ammonia is much more electronegative. And so it really strips the electron cloud off hydrogen. Well, if the electron cloud gets stripped off hydrogen, hydrogen has what charge on it? Yeah, in the nucleus, it just has one proton in the nucleus. So if we look at the proton in the nucleus, and the electron cloud's been stripped away, that's a partially exposed proton. Partially exposed proton. Partially exposed proton has about a +1 charge. Whereas this proton's different. This one's shielded. And so the charge is delta plus, not a full +1. So if you're out over here, you see a full +1. If you're out over here, the +1's shielded. That is, there's a negative charge cloud around it that blocks off some of the positive charge. And so we can get a partially exposed proton when we have nitrogen, oxygen, or fluorine bonded to hydrogen. Anything else won't partially expose it enough. And so we end up with a shielded proton here. The higher the charge, the stronger the electrical attraction is going to be. Of the three types of intermolecular forces, which one operates in all molecular substances? London. Which one operates between all polar molecules? But not necessarily all molecules. Between all polar molecules, they're all going to have what force? They're all going to have dipole. All right, take a look at A and tell me what the primary, all these, A through D will all have London. Okay, is London the primary or is something else the primary force for A?
A has a hydrogen bond.
A has hydrogen bond? Yeah. This is ethanol. Ethanol can hydrogen bond. This is why ethanol and water mix so easily. They both can hydrogen bond. So A, ethanol, hydrogen bond. B. B is dimethyl ether.
Let's say CO2 because, eventually because the oxygen is not electronegative, so it's stronger.
Well, what you're doing when you're what are you doing when you're melting something? Are you? Yeah, it depends on what you're melting. If you're melting what we call molecular solid, like dry ice, say dry ice is hard to melt because it does something called sublime. When we melt something like dry ice, we have to break the molecules apart from each other, and so we have to look at what's holding the molecules together. And so in this case, there's going to be intermolecular forces of attraction that hold two CO2 molecules together. And then what we're comparing that to are the intermolecular forces of attraction that hold two CS2s together. Now, what are the intermolecular? Do we have hydrogen bonding here? No. Do we have dipole forces here? Dipole, no. No dipole, that's correct. So we only have dispersion for both of them. And so which one has a higher melting and boiling point and why?
CS2 because the S is more electronegative.
No, oxygen is more electronegative. You're right. CO2 is going to have bigger dipoles than CS2. CS2 is going to have smaller dipoles because oxygen is more electronegative. Well, what impact is that going to have on its boiling point? Is it going to make stronger instantaneous dipoles? Yeah. Either of them.
CO2 will have stronger instantaneous dipoles and they'll be harder to break.
CO2 has larger permanent dipoles here. But the instantaneous dipoles, they fluctuate. Which one do you think will have the bigger fluctuations that can generate bigger? CO2, why is that? Has more dipole to work with? Yeah, I guess. When I think about this, I think about electron cloud. Which one's going to have bigger electron cloud? Well, oxygen is more electronegative. It's going to polarize it like this. Well, I think, okay, how many electrons total does oxygen have? Not valence, but total. So it has 6 valence electrons, but a total of 8. There's 2 core, 6 valence. How about sulfur? Yeah, sulfur has a total of 16 electrons. And so when I look at the electron cloud here, it's a lot bigger, although it's not as polarized. It's a bigger atom. Sulfur is a bigger atom, bigger electron cloud. On average, we're going to get a dipole like this. But let's say all 16 electrons decide to go to sulfur. If all 16 electrons go to sulfur and leaving carbon nothing, then this dipole grows. Versus over here, how many electrons would go to oxygen? Let's say all 8 electrons go to oxygen. And so which is going to set up a bigger instantaneous dipole? Having 8 electrons move over to oxygen or having 16 electrons move over to sulfur? 16. And so this is going to have bigger even though the permanent dipole here is smaller, the instantaneous dipole can be much bigger. Over here, the instantaneous, even though the permanent dipole is bigger, the instantaneous dipole isn't going to be that much bigger. Does that make sense? And so this is going to have the higher melting point and the higher boiling point because it's going to have more electrons. More electrons means bigger polarizations are possible in the electron cloud.
So what's the difference between electrons and valence electrons?
Well, I'm talking about just the total electrons because even the core electrons can become polarized. So the core electrons are in the 1s orbital, and let's say in the 1s orbital is spherical, but let's say they all move to the left side or the right side of the 1s orbital. And so we include all electrons, the core and the valence. And so the number total, if you look at oxygen is element number 8, so it has 8 protons and 8 electrons. Out of those 8 electrons, 2 are core and 6 are valence. So we look at the total number of electrons. If we compare just the valence electrons, then both of these have the exact same number of valence electrons. And so there'd be no difference. Sulfur has 6 valence electrons, oxygen has 6 valence electrons. And so then we wouldn't be able to differentiate the two. Okay. Select the best answer to complete the following statement. The boiling point of ICl, iodine monochloride, or monoiodine monochloride, is higher than the boiling point of bromine because, so ICl has a higher boiling point. Okay, so which one's the best answer? A, the molecular mass of ICl is 162.4, whereas that of bromine is 159.8. And so this is a little bit tricky because oftentimes people will say the higher the molecular mass, the higher the boiling point. But it's not because it weighs more, it's because it has more electrons. And so the higher the molecular mass, the more electrons. More electrons means the more polarizable the molecule is. And the larger instantaneous dipoles we can set up. But is it that much heavier? That is, do you think it has that many more electrons? Actually, let's just take a look. Bromine is 35, so 2 bromines would have 70 electrons. And then iodine with chlorine would be 53 and 17 with 70 electrons. And so ICl has 70 electrons, and bromine has 70 electrons total. B, there is hydrogen bonding in ICl. Is that true or false? That's false. C, ICl is an ionic compound. No, metals and nonmetals are ionic compounds, so we'll eliminate C. D, ICl is polar while bromine is nonpolar. That's true. ICl. E, induced dipole forces are much stronger for ICl than for Br2. Well, ICl, we did the electron count, 70 electrons here, so, it's not going to be that big of a difference. And so I think the best answer will be D. Predict which compound, methane or fluoromethane, has the higher vapor pressure as a liquid at a given temperature. Explain your prediction. So vapor pressure is the opposite. The weaker the intermolecular force, the higher the vapor pressure, or the stronger the vapor pressure. Because vapor, to get a big vapor pressure, we want it to vaporize easily. And so this is asking which one of these two will vaporize more easily, methane or fluoromethane? Methane. Methane only has dispersion, whereas fluoromethane has hydrogen. This is tricky because does fluoromethane really have hydrogen bond? No, it's because all the hydrogens are bonded to carbon. And the carbon's bonded with fluorine. And so it would be dipole. Predict which compound, SO2 or CO2, has the higher vapor pressure. Which one vaporizes more easily? The one that vaporizes more easily is more weakly held, less sticky. CO2 or SO2? We're talking about it over here. So which one of these is going to have a weaker force holding the two molecules together? CO2 is going to have the weaker force, and why?
There's less electrons.
Less electrons. Less electrons means less polarizable and smaller instantaneous dipoles. Less electrons over here. More electrons, more polarizable, bigger instantaneous dipole. So this is going to be stronger, more sticky. This is going to be weaker, less sticky. And so this is going to have a higher vapor pressure because vaporization, we want it to vaporize them. Those are the types of questions. When we vaporize it, there's something called the liquid vapor equilibrium, which we'll look at next. When something vaporizes, it's going to depend on the strength of the intermolecular forces. So, do you know what this curve is showing or trying to represent? This curve is trying to represent the energy. Let's say I have a sample of liquid CO2. So CO2 liquid at a given temperature. CO2 is hard to liquefy. But let's say I have liquid CO2. Are all the molecules of CO2 moving at the exact same speed? No. They aren't. Even though this is at a given temperature, at T, what we see is a distribution of energies. Like this. And it's going to have this characteristic shape. The shape of this distribution kind of looks like a bell curve with a shoulder on it. Do you see that? This is called a thermal distribution. There are different names for this. Thermal distribution. Temperature distribution. Actually, temperature distribution is probably not the greatest word. There's kinetic energy distribution. Boltzmann distribution. Maxwell-Boltzmann distribution. So let's take a look at the Maxwell-Boltzmann distribution here. This is a very famous distribution, the Maxwell-Boltzmann distribution. This is Maxwell-Boltzmann distribution at different temperatures. This is the same population. And so on the y-axis, we have the population. You can see the highest population will be here, and it'll have this energy. This is for a lower temperature distribution. So this is going to be at temperature A. Let's say temperature A is a room temperature. Or maybe the red one. Let's say the red one were at room temperature. If the red one's at room temperature, not all the molecules are moving. We're going to have a distribution of energies. Most of the molecules are moving at this energy here. There's a very small population of very high energy molecules that extend out here. It's a very small population. And then we have something called the average, or the root, kind of the effective. If you gave the entire population one kinetic energy, that one kinetic energy would be here, let's say. And we call that the root mean square kinetic energy there. And so we treat all these and average it. The average comes out on this shoulder here. Okay, if we did the same thing here, the average would be out here because it's skewed towards higher energy. It wouldn't be at the peak here because it's asymmetric in its shape. And so if we take this as a room temperature, cool it down, the population shifts left. If we warm it up, the population shifts right. The area of the curve stayed the same because we're not going to add any to the population and we're not going to remove any from the population, any molecule. So there's going to be a certain minimum energy required for vaporization. And that depends on how sticky the molecules are. If the molecules are really sticky, that is, they have strong intermolecular attractions, then the cutoff here is way up here. And so very few molecules will vaporize. Okay, as the intermolecular forces, if they're weaker, then the energy shifts over here, and we're going to have a much greater population that can vaporize, depending on what the energy is that's required for vaporization. And so let's take a look at this. That's what they're showing here. E is the energy required to vaporize a molecule. It has to have this amount of energy to break off the surface. And so the population that can break off the surface is shaded here. These molecules don't have enough energy to break the surface, break from the surface, break free from the surface. And so that's the number of molecules having enough energy. Now, if we change the temperature, it'll either increase the population or decrease. So if we lower the temperature, the whole population shifts left. And that means this is going to shrink. If we increase the temperature, the whole population shifts right, and that means this is going to grow. And so we can change the vapor pressure with temperature here. So here, this is just water in an Erlenmeyer flask that's been capped with, and there's dry air in here. If it's dry air, there's no humidity. Initially, this is going to be at one temperature, let's say room temperature. And room temperature, there's enough energy to vaporize a certain population. And so that's going to stay the same. As long as we keep the temperatures the same, the amount of molecules that can vaporize will be fixed. That's a fixed percentage. What's going to change is this, the reverse. So as the population of gaseous water molecules increases, the reverse process can occur, which is condensation. So water molecule comes over and sticks onto the surface. And if it gets stuck on the surface, that's called condensation. The greater the population of gaseous water molecules, the greater the probability of sticking, that is, condensing onto the liquid surface. Eventually, we'll hit a point where the population of gaseous molecules gives a rate of condensation that's equal to the rate of evaporation or vaporization. And so initially, when we have dry air, the condensation rate is 0, and evaporation takes place. As more evaporates, the rate of condensation increases here. It continues to increase until we hit this max. This max is a state of what we call dynamic equilibrium. Evaporation continues, condensation continues, but it's going around in circles. Nothing's really changing. So the amount of liquid water here stays the same, and the amount of gaseous water stays the same. However, it's always changing because the molecules, water molecules, are cycling back and forth between gaseous and liquid state. And so we have a dynamic equilibrium here. And so read this and understand that. All right, so we're going to continue with this chapter after a break. Let's take a break now, and we'll look at the rest of chapter 15. Okay. So what we're going to do, this is pretty long. We're going to do parts 1 and 2 for this. For part 1, we're going to deal with known solutions. That is, we'll know what's in it. And part 2 will deal with unknown solutions. And the whole point of qualitative analysis is just to identify what's present, qualitatively. If it's quantitative analysis, then we want to identify what's present and how much. Here, we don't care how much. We don't care what the concentration is. Just, can we detect it or not detect it? Now, qualitative analysis suffers from different problems. One of the problems in qualitative analysis deals with the sensitivity. It might be present, but the test isn't sensitive enough to detect. That is, if it's too dilute. Some of the tests are quite sensitive, and so we can easily see if we have a positive test result, then we definitely have it there. If we have a negative test result, then it depends on the sensitivity of the test. If we get a negative test result, it might be there, it might not be there. It's like if you take your COVID test and you come out negative, and you think, okay, I don't have it, right? But it depends on how sensitive that test is. Did you get the PCR test or did you get what's the other one? Antibody or antigen test, And so it varies. And the same thing here. Some of the tests are too sensitive, so you might come up with a false positive. Well, in this case, if you get a positive here, it could be a false positive due to cross-contamination or those types of things. And so we got to worry about, what positive means, what negative test means. So this is qualitative. Okay, what are we testing? We're going to test a water sample. We're going to test a water sample for the presence of ammonium, silver, lead, 2, barium, manganese, 2. These ions. We're going to test a separate solution for chloride, sulfate, and nitrate. And so we're going to have 2 separate solutions. One's going to be the cation, one's going to be the anion solution. This cation solution is not going to have individual ions in there. And it's just going to be a mixture. And so in your cation known solution, you have all of these cations present, all 5 of them. And so if they're present, what that means is you should get positive test results for each of these. And so this is what we're going to do. We're going to go through a run through and make sure we get a positive test result and see what a positive test result for each of these looks like. Okay, after we do that, then we're going to run our unknown. Our unknown won't have all of these. And so based on our observations from the known, we'll try to figure out what's present in the unknown by seeing what comes out positive. The unknown's a bit more complicated, and since the known has everything, then we'll go through all the steps. In the unknown, since it doesn't have everything, let's say it's a 3-step procedure to figure out silver. Are we going to do all 3 steps if silver is not present? No. And so what we have to do for the unknown is we have to modify the procedure to suit our unknown. And so that makes it difficult. Our unknown is also going to have the anions included with it. And so it's going to be a cation and anion mixture. Whereas our known is going to be 2 separate solutions. So this is stuff you can just read through, basically, here. But you want to read through it, otherwise you'll be confused. And there's not much time to read through it in lab. So you don't want to sit there for the first hour of lab trying to figure out what's going on here. And so we'll read through this initially. So you read through this, and it boils down to this. We can look at all the reactions here. Boils down to a flow chart like this. You're going to get more than 12 milliliters of cation mixture. Don't use all your cation mixture for this test here. Likewise, okay, how many cations were there? There were 5 cations. 1 cation is missing here. It's still there, but do you know what cation is missing? Ammonium. Ammonium is missing here. The reason ammonium is missing, it's still present here because it contains ammonium, but the reason it's missing is because we're going to test ammonium separately. We're going to do what's called an individual test for ammonium. And so this is the ammonium test. And so this is going to be a separate test tube, 3 milliliters. 3 milliliters is about 3 squirts of the plastic pipette, or about 3 thumbnails. Don't get your grad cylinder and measure it out. It's a waste of time. We don't want to waste time in this lab. The sooner we can get through this, the more time we have to spend on our unknowns. And so we get a test tube and put about 3 milliliters. It doesn't have to be exact, anywhere from 2 to. Don't go too much more. Sometimes going more gives more precipitate, more gas, more whatever, and so it's easier to see. But on the other hand, sometimes using more wastes a limited amount. And so just use 3 milliliters here. And then what we're going to do is we're going to add sodium hydroxide. Sodium hydroxide and ammonium react. In fact, ammonium is a weak acid, and hydroxide is a strong base. So when ammonium reacts with hydroxide, it forms ammonia gas. And that ammonia gas we can test with litmus paper. So if you test air with litmus paper, air is not acidic, it's not basic. It consists of nitrogen and oxygen. And so litmus paper is not going to have any impact. But if you test ammonia is a weak base, and it should turn litmus. Litmus is a pH-sensitive dye. And so it should turn red litmus blue. So this is what they mean by blue litmus here. But we have to be careful. I'll talk about how we're going to set this up. Now, I usually like to just go off the flow chart here. And so this is what I do to prepare for maximum speed in lab. So I'm testing for ammonium. This is the ammonium test. Here. And so I have a solution here. And then I'm going to add sodium hydroxide to this. And then what that's going to do is it's going to convert my ammonium to ammonia. And then I'm going to test this. The ammonia is very polar in a hydrogen bond, so a lot of it is aqueous. But what we need to do is we need to get it in the gas phase. So sometimes if you heat it or shake it, you'll drive off some ammonia gas. So we can read the procedure here. Let's see what the procedure says in the ammonium test. One, the cation tests except ammonium are carried out as part of a continuous sequence of steps with one large portion of solution. See flowchart, page 7. Okay, the ammonium is just going to be individual. So we'll scroll up here and let me read the procedure for ammonium. That's A here, identification of ammonium ions. This is the only cation tested with a separate sample solution. Attach a moistened piece of red litmus paper to the convex side of the watch glass. Pour 3 milliliters of cation mixture into a 100 milliliter beaker. Add 3 milliliters of 6 molar sodium hydroxide and quickly cover the watch glass. Swirl gently, taking care not to splash the litmus paper. And so what I do is this is the way I like to do it. I like to do it like this. We're going to put it into a 100 milliliter beaker. So I'll just write 100 milliliter beaker, or I won't even write beaker, maybe just 100 milliliter and draw a picture of a beaker or something like that. And then we're going to put 3 milliliters of unknown aqueous. Unknown aqueous is just our unknown solution. So we get that 3 milliliters in here, and then how much sodium hydroxide do we add?
Mm-hmm.
3 milliliters. This is like 3 squirts. 3 milliliters of 6 NaOH, 6 molar sodium hydroxide. Okay, then we're going to cover it. Okay, I'm going to cover it like this. This is a watch glass here. And then we're going to stick a piece of red litmus paper on the bottom of this. Well, it's not going to stick unless it's wet. Wet litmus it's like wet paper. Wet paper adheres. Wet paper lights glass, the adhesive forces. And so that's red. Now, this is going to be the ammonium plus hydroxide what reacts. So writing just the net ionic equation here, ammonium and hydroxide will form ammonia and water. Hopefully some of this ammonia will rise up as a gas. That's what we want to happen. So we want some of this ammonia to rise up as a gas, NH3 gas. If hydroxide gets on our red litmus, it'll turn it blue. So we don't want any splashes to hit our red litmus. What we want is we just want the ammonia gas. And so the ammonia gas comes and hits the red litmus. Red litmus is an acid. The anion is kind of complicated, so I'm not going to draw it. And so when ammonia reacts with litmus, it takes the proton and leaves us with Lit minus. This is blue. So in other words, when litmus is protonated, it's red. When it's deprotonated, it's blue. When red litmus is in acid form, it's red. In base form, it's blue. And so we want the ammonia to rise up and then hit. And so what we should see is a gradual color change. It should slowly fade to blue. And eventually it'll be a deep blue. If you splatter this, then you're going to get splotches of blue from the hydroxide hitting it. The hydroxide can also neutralize the litmus. And so what I do is I don't bother reading. I just look at my drawing and then this is it. And so if I get this to turn blue, this is what we call positive test for ammonium. Ammonium must have been present in my unknown here to give that. It's actually a positive test for ammonia, but really what I'm looking for is ammonium. I don't have ammonia in my unknown. Does that make sense? Yeah. Okay. So I do this so I don't have to read this. This is too long. Yeah. Now, what they're talking about in the rest of this is that hydroxide not only reacts with ammonium, hydroxide reacts with the other cations in the mixture. And so these are called interferences. Interferences can tell you what other species might be present. And so what are the other cations present in the mixture? For example, silver. Silver and hydroxide like each other, and they'll form silver hydroxide as a precipitate. This would be the NIE, the net ionic equation for this. Two silver hydroxides can decompose into one silver oxide plus water. And so we end up with a black precipitate. This is interference with silver ion in this test. So what we might see is we might get a black precipitate in here. And that gives you a clue, hey, there's probably silver inside here. We get a black precipitate. Unless something else gives us a black precipitate. Well, lead might be in here. Silver and lead are heavy metals, so you can watch out. Probably want to wear gloves tomorrow. Lead likes hydroxide. Two hydroxides to form lead-2 hydroxide. But lead-2 hydroxide is a white PPT. So if you get both a black PPT and a white PPT, it's hard to tell the color because this is going to be all mixed together. It's going to look. Or if you just get a white PPT, maybe there's no silver present. So if you in this interference, if you only get a white PPT, then that's telling me there's probably no silver in there. There's probably no manganese. Probably only lead. If manganese is present, then manganese likes hydroxide, manganese 2 ions. Manganese likes to form +2 and +3. So this is manganese 2. You're going to form manganese 2 hydroxide. Manganese 2 hydroxide is a lead-brown PPT. One of the things that happens, I don't know, every semester, somebody dumps all 15 milliliters of their unknown for just this one test. The stockroom, they're not happy about that because they have to make more chemicals, et cetera, et cetera. So they're going to be pissed off. So just make sure you only use 3, unless you have to repeat it. All right, so I kind of approach the rest of it like this. So we do a separate test for ammonium. Now the rest of the ions, silver, lead, manganese 2, lead 2, manganese 2, what else? Barium. How do we test for those? We test for those on the other flow chart. And so this is part B here. Part B is going to be the other flow chart, which is 12 milliliters. Place 12 milliliters of the cation mixture in a large test tube. Add 3 milliliters of 6 molar HCl. So what I do is I don't want to read through this. And so what I'm going to do is I'm going to just get the flow chart. Either I'm going to copy the flow chart into my notebook or make a photocopy of this and then just use this as is. You don't have to prepare the entire experiment, but you should prepare, the first part of the experiment so things go more smoothly in lab. So this is going to be for silver, lead, barium, and manganese analysis. Now the dashed lines here means solution. The solid lines means precipitate. And so it's 12 milliliters of cation mixture into a large test tube. So what I do is this. I have the flow chart here, and I primarily use the flow chart, 12 milliliters of unknown aqueous. That's a cation mixture. And so I'll just draw like a large test tube here, and then just dump all 12 milliliters in there. And then to that, we're going to add HCl. Well, how much HCl and what concentration? That's what I want to know. How much and what concentration? So I go back up here. And I take a look. It says to 3 milliliters, add a few drops of 6. Oh, that's not it. I need to go back up more. Here it is. Add 3 milliliters of 6 molar HCl. If any precipitate forms, heat the mixture in hot water bath. If part of the precipitate is lead 2 chloride, that part will dissolve when the mixture is heated. So there are actually 2 steps here. One, we're going to be adding our HCl, but what are we trying to do with this HCl? What we're trying to do is this. Let me show you on the flow chart. This flow chart is not detailed enough. Step 1, add HCl. Step 2, heat it. So let's take a look at step 1. What we're trying to do with chloride is to form a precipitate. Chlorides are all soluble except for silver, lead, mercury. Actually, just only silver, lead, and mercury. Sulfates would have been done. And so this one, silver and lead should precipitate, both. Okay, so this one thing I'm going to modify is I need this to be 6M HCl. And the other thing I need to modify is it says to add 3 milliliters, but I'm not. Well, maybe I am. What we want to do is we want to add this here to maximize precipitate. And so what we're going to do is we're going to get two precipitates here. So it's going to turn cloudy. The two precipitates are going to be silver chloride, solid, which will precipitate. The reaction there is Ag plus chloride makes silver chloride. This would be the net ionic equation for that. Silver and chloride like form precipitate. And the other precipitate that's going to be in here is PbCl2. Now it's tricky because this is going to be all cloudy white. And so what you need to do is you need to add it slowly. If no precipitate forms, then don't add all 3 milliliters.
Would it form immediately?
Yeah.
Before.
Yeah, you'll see it immediately form. So if it stays colorless and no cloudy precipitate forms, you don't want to add all 3 milliliters because it's going to screw things up. That's going to lead to interferences later on, which could cause false positive test results. And so we need to tailor this experiment a little bit. For your known, it's not that big of a deal because your known has these ions present. But what if your unknown didn't have any silver or lead? If your unknown didn't have any silver or lead and you're adding that much chloride, it's going to make your life more difficult later on because that chloride could potentially interfere in subsequent steps. The other thing is how much? How do we know when to stop? In the titration, we knew when to stop because the color went from colorless to pink. How do you know when to stop here? How do you know when you've precipitated all of it? So what they did was they came up with some general amount, 3 milliliters. They thought, okay, 3 milliliters, that should be enough to precipitate everything. But how are they so sure it's enough to precipitate everything? Or it might be way too much to precipitate everything. And so what we do whenever we have a precipitation, we do this. We keep adding. It doesn't matter how much I add. Let's say I added 3 milliliters and I stopped, but it's still precipitating. So if I had 4 milliliters, I'm getting more. If I had 5, I'm getting more. If I had 6, I'm getting more. What I need to do is I need to make sure all the silver and the lead are precipitated out in this step. Because if they don't, then if the silver doesn't all precipitate, then the silver ends up here. If the silver ends up here, it screws these tests up. Because those are interfering. Silver is a potential interfering ion in subsequent steps. So a lot of the problems, people get these very ambiguous results like, oh, I'm expecting this, but I'm not getting it. Well, you're not getting it because of these things that happen. You didn't do a complete separation. What we need to do is that we need a complete separation. Well, how do you know? Well, what you do is you keep adding it until it stops precipitating it. Once it stops precipitating, then you're done. That's enough. It could be half a milliliter or it could be 10 milliliters. Whatever it is, you keep adding until it stops precipitating.
Do you recommend swishing it around?
Now, that's the problem because the more you swish this around, the more cloudy. It's like a fog. How can you tell if it's getting foggier or not foggier? It's hard to see because it's already so dense. This is so dense and cloudy, it's hard to see if any precipitate forms. And so what we're going to do is we're going to heat this in a water bath. When we heat this in a water bath, we have something called a hot plate, so you don't have to set up a burner. We'll probably put some hot plates. You get a beaker of water, put the beaker of water on the hot plate, and then heat it. Don't let the beaker go dry. And then we're going to put our test tube in that beaker of hot water and then warm up the solution. There are 2 reasons we want to warm this up. One reason is to coagulate the crystals. So if you have tiny crystals, what we want to do is we want them to grow into bigger crystals. To make them grow into bigger crystals, we got to get them to collide and stick to one another. And so that's called coagulation. When we coagulate this, what happens is it forms bigger crystals which settle down due to gravity. And so as they settle down, the top portion becomes clear and the bottom portion becomes cloudy. As soon as the top portion becomes clear, add another drop of HCl. So once this clears up on the top, I'm going to add a drop of HCl and then see if it turns cloudy. If it starts to turn cloudy, then I have not done. I got to add more HCl. If no cloud formation appears, then I'm done. You know, I precipitated out all of it. Does that make sense? And so when you're doing the precipitation, it gives you some, you know, this is it. If you don't understand what's going on, follow the instructions. But there's something that you can do to modify the instructions to make it go a lot cleaner, so you get really good results. Okay, so what we're going to do is we're just going to add until it stops precipitating. Once it stops precipitating, then we're good. So the first function of heating it is to coagulate. The second function of heating it is this. Lead 2 chloride is much more soluble in hot water than silver chloride. So if I have a hot water bath here, okay, at this point I don't want to stir it because when I stir it, it just makes it cloudy. And so you want to let this settle down to the bottom. Over here, I want to stir it. So I'm going to get my glass stirring rod and then stir this and try to crush up the crystals. Because what I want to happen is I want the PbCl2 solid to dissolve in hot water to form PbCl2 aqueous. PbCl2 aqueous consists of Pb2 plus ions and chloride ions. It's a strong electrolyte. So we can dissolve this in hot water. Whereas the silver chloride does not dissolve in hot water. Well, a tiny bit dissolves, but it's negligible. And so when the silver chloride is mixed with the hot water, it stays as a precipitate, silver chloride solid. It does not dissolve. And so in this step, we need to dissolve it. To dissolve it, you got to crush up the crystals to get them to dissolve. It's like trying to dissolve sugar cubes, you know, really, really tiny ones. You want to crush them up, see if they'll dissolve in the hot water. And so this is 2 steps here. 1, precipitation, the max. 2, heat, coagulation, and for dissolving the lead. Now, the lead dissolves. We got to make sure we do this. We're going to separate this while it's hot. And so we're going to do a filtration, a gravity filtration step here. In gravity filtration, we'll get our funnel and a piece of filter paper. I'll talk about the filter paper tomorrow in lab.
Oh, so we're going to separate it?
Yeah, we're going to separate it. Okay, then we're going to filter the mixture. This is going to be a heterogeneous mixture. It should be hot. If the mixture cools down, do you know what's going to happen?
Lead 2 is gonna.
The lead, yeah, is going to come back. It's going to precipitate. So we need to filter this hot. Well, the hot silver chloride is going to be solid. And so we're going to capture the silver chloride on the filter paper. And then the rest of the stuff is going to go into, you know, a beaker or whatever you have as a catch container. And so we end up with something called the filtrate. The filtrate is the liquid phase. Hopefully the lead stayed dissolved. And then we have our manganese and the barium. Right? Yeah. But the problem is this. The silver chloride solid is wet. It's contaminated with filtrate. Contaminated with filtrate. And so we need to wash our precipitate off. When we wash our precipitate, you should use your hot water bath with DI water. It probably says to use tap water. Or you put another test tube in your hot water bath. Actually, it's probably good. Put another test tube in here and fill it with DI water. DI water for washing. Now, if we wash this with cold water, what's going to happen is the lead is going to precipitate out and it's going to be captured. So we're going to contaminate our silver chloride. It's going to be a mixture of silver chloride with lead chloride. And so what we need to do is we need to make sure we wash with hot water. And so this is going to be the hot water that we're going to use for washing, and it's going to be sitting on the hot plate. So wash with hot water. On the one hand, we want to wash with lots of hot water. The more hot water we wash this with, the purer our silver chloride is going to be. On the other hand, we want to wash with a minimal amount of hot water. The reason we want to wash with a minimal amount of hot water is because the more hot water we add, the more dilute these ions become. And the more dilute these ions become, the harder they are to detect. Because some of these tests just aren't that sensitive. And so if we keep diluting this and diluting it and diluting it, eventually it becomes so dilute, we get a false negative.
When you say wash with the hot DI water, do you mean put the DI water in the bath, take it out and pour it down the funnel, or take out the filter paper with the...
No. Leave the funnel and filter paper here, and then take it out of the bath using some test tube clamps and just pour some in there.
Okay.
And we'll just pour a little bit here, a little bit more. We want to wash off all the white precipitate, make sure there's no lead on here. If there's lead on here, it's going to screw this up, this test here. If there's lead on here, it's going to screw not only the left branch up, but it's also going to screw up the right branch because we're going to have too little lead to detect the right branch. And so we wash. Now, how much is a reasonable amount to wash with? So let's see what the procedure says as far as the washing step goes. So we're at washing. Under the experimental notes, washing precipitates use only distilled water. Well, unfortunately, we don't have any distilled water. We're going to use deionized water because tap water contains interfering ions.
You could bring distilled water, right?
Yeah, you could bring distilled water, but not really necessary. Okay, let's read what the procedure says to do about the washing. If lead-2 ion is present, it will begin to form a white precipitate as the filtrate from step 1 cools. If a white precipitate forms, warm this mixture gently in a water bath. Okay, what this is saying is this. After you filter this, this is going to look nice and clear here. But as it starts to cool down, and you have lead there, the lead is going to precipitate. So this is going to turn cloudy with precipitate. This is lead-2 chloride, so don't filter it in. So what they say is if you get a precipitate in your filtrate, then what you need to do is you need to warm this. But let me go up. I think I skipped some steps here. Okay, here's the washing step. Wash the precipitate from step 1 once with 5 milliliters of hot water. Remove any PbCl2, which may remain. not only the PbCl2, but also the manganese and barium. Discard the wash water. Add 5 milliliters of 6 molar sodium hydroxide in the precipitate, which is on the filter paper. Okay, this is combining steps here. And so what we're going to do is we're going to wash. Normally what I do is this. The first wash, I let drain into the filtrate. I normally wash it 3 times. And so maybe I'll use less than 5 milliliters. So the first wash, collect it. The second wash, throw it away. So what I'll do is I'll remove this beaker and place a waste beaker here. And then I'll do a second wash and a third wash with hot water. The first wash is going to give you the highest concentration of lead, manganese, and barium. And so that's why we want to keep it. We don't want to lose that. And so I'll just use a minimal first wash. Save it with my filtrate, which contains lead, manganese, and barium. And then do a second and third wash here. Okay, after I do the second and third wash, the waste beaker is still going to be here. And then what I'm going to do is I'm going to dump in some sodium hydroxide in there. What the sodium hydroxide is going to do is it's going to turn my precipitate black. And so I'll have a white precipitated silver chloride that's clean, it's washed so it's fairly pure, and then add my sodium hydroxide. I don't want this to go into my filtrate over there. So this is going to go into a waste beaker as it drips down through the funnel. But what it is when it contacts the white precipitate, it turns the white precipitate black. And so it converts silver chloride into silver oxide here. Once I get the black silver oxide in the filter paper here, turn the precipitate black inside here, then that's a positive test for silver. Okay, then I'm going to analyze my filtrate. When I analyze my filtrate, okay, I take it over here, and then I'm going to test for lead. So do you see what I'm doing here? How much sodium hydroxide do I add? I don't care how much sodium hydroxide. I add enough to see if I get a black precipitate or I don't. So just squirt it in there until you're absolutely sure. How much Ki do I add? How much Ki do I add? I add enough to make sure I get complete precipitation. I don't care how much that takes. I just keep adding until it stops precipitating. Now, it's going to be hard because it's going to be cloudy. So what I might have to do is I might have to stop and let the precipitate settle down. If the precipitate settles down, then I'll get a little clear layer on the top, add 1 drop on the top and see if I get more yellow PPT. If I get more yellow PPT, then I just keep going. And then eventually what's going to happen is it's going to settle. You'll get a clear layer on top. You'll add a drop of Ki, no precipitate. Then you know you're done. You've gotten all the precipitate. Okay, then once you have all the precipitate, then what do you need to do? You're going to filter it. And so I'm going to I'm going to separate my precipitate from the filtrate. And so the same thing applies here. I'm going to get a clean sheet of filter paper, clean funnel, and then I'm going to filter this out. But here I'm going to wash it. The first wash, I want to make sure I don't lose any barium and manganese because this is going to be contaminated with filtrate solution. So I'm going to wash off the filtrate using a little bit of wash and then collect it here so I don't lose any. The second and third wash I'm going to discard because by the second and third wash, there's very little barium and manganese left on my precipitate. Does that make sense? Yeah. Okay, this is the end of the line here. So if we get a yellow PBT, then that's positive for lead. I'm not washing it, in this case, to clean it. So I only need to do the first wash. The second and third wash are to really get it clean, but it doesn't need to be really clean. It's either yellow precipitate or not. So the first wash is just to make sure I don't lose any barium and manganese over here. Let's save it. Okay, now what I'll do is, okay, I'm done with the lead. You're going to get a yellow precipitate for your known. Now I'm going to test for barium and manganese. And so I have this solution here. I'm going to add sodium bisulfate. Let's see what happens here. Okay, am I adding sodium bisulfate solid or solution? So is this Ki solid or solution? So I want to know that. Its solution. Both of these are solutions. We're only going to have one concentration of these. HCl, we have multiple concentrations of that, so it's important to write the concentration of those. But the same thing here. How much sodium bisulfate do I add? I don't care what it says in the instructions. You know how much I'm going to add? Yeah, I'm going to keep adding until I stop getting white precipitate. That's how much I'm going to add. Once I stop getting additional white precipitate, I'll stop adding that. Okay, here I'm only going to collect the first wash. I'm only going to collect the first wash because I don't want to lose any manganese that might be adhering to the crystals here. So I'll just do a small first wash, dump it in with my filtrate. Second and third wash, I'm not going to bother, because this is the end of the line. I did a second and third wash up there. The reason I did a second and third wash up there on the left is to minimize any contaminants from interfering with that second step. Here, there's no second step. We're done. All right, now we're down here. And so I'm going to add sodium hydroxide. How much sodium hydroxide do I add? Yeah, as much as required to precipitate. And so I just keep adding. Now, you have to be careful, because the amount, it's not necessarily going to start precipitating right away. It's not going to start precipitating right away because sodium hydroxide is a powerful base. But sodium bisulfate, bisulfate is on this chart. You see it here? It's one of the stronger weak acids. And so this is very tricky and deceptive because first the sodium hydroxide has to go into neutralizing any extra bisulfate you might have added. Once you've neutralized any of that acid, then it will start to precipitate. So in the procedure, it asks you to check for litmus. The only time you really need to check for litmus is in the ammonium test. All these subsequent times, just keep adding until you get the precipitate, basically.
What's the molarity of these solutions?
The molarity, the ones that are important to pay attention to the molarity will be the acids and the bases. So we want to know the molarity of this. The sodium bisulfate, we only have one solution in lab. Sodium hydroxide, we have multiple. So we have 0.1 molar, 6 molar, 12 molar. We got to make sure we use the right molarity for that. And so sodium hydroxide is probably going to be 6 molar. This is what you read the procedure, and then you can write this on the flow chart. Anyway, this light brown precipitate is very hard to see. And if you have too much water, you're not going to get very much of this. And so this is tough. And so what we're going to do is we're going to capture this in our filter paper. The light brown precipitate is very wispy. And then we're going to test this light brown precipitate. We're going to do additional steps here. The first step is we're going to dissolve that light brown precipitate. And so what I need to do is I need to take the filtrate and discard that. And when I add nitric acid, the nitric acid dissolves this precipitate and creates a solution, manganese 2 solution. And so what I'm going to do is I'm going to add the nitric acid to the filter paper. The nitric acid dissolves the precipitate, and then we let the precipitate drain into a beaker or test tube here. Okay, once I dissolve all my light brown precipitate, I have manganese 2 in solution. And then what I'm going to add is this stuff, NiBiO3. NiBiO3 is called sodium bismutate. Be careful with this because sodium bismutate is a powerful oxidizer. And so we add this. This is solid, and it's a powder. And so don't create a dust cloud of sodium bismutate. If you create a dust cloud, then people are going to inhale it, and it's very corrosive. And so be very careful with the sodium bismutate. If you spill some on the counter, clean it up with a wet cloth. Okay, try to avoid forming a dust cloud at all costs. Okay, now with the sodium bismutate, we're going to mix that in with our nitric acid and Mn2 plus, and what that's going to do is it's going to convert Mn2 plus. Mn2 plus is a very light pink color, and it's going to convert it into this ion. What's this ion called? MnO4 minus. Permanganate. And permanganate has a deep blue, not blue, deep purple color, and so it looks like grape juice. And so if you see grape juice liquid, then that's positive. It's a positive test. You're looking for a liquid that is the dashed line, aqueous solution of grape juice. If you don't, sodium bismutate is like, we just use a little bit. And you use a little bit. If you don't see it, then you add a little bit more, but use this stuff sparingly. All right, so that's the bulk of the lab there. We're going to spend time analyzing the cation. What I recommend is the ammonium test is quick and easy. So I recommend just starting on this part first. Save some for the ammonium test later. You can do the ammonium test when the water is boiling or something like that, waiting for the water to boil. But this one takes time. So start with part B and the silver analysis. Okay, the others are all one-step deals. So ammonium test is one step. The chloride test is one step. The nitrate test is one step. And the sulfate test is one step. And so these are quick and easy. I'll talk more about those later. This one is more difficult.
I have a question. For the silver, when we make the silver oxide, do we take the filter paper out?
No. Leave the filter paper in.
So we pour the sodium hydroxide into the
Right on top of it. Yeah.
And does it go? Do we want it to go down?
We don't want it to mix with the filtrate. So what you do is you remove the filtrate beaker and you put a waste beaker there. Otherwise, the sodium hydroxide is going to interfere with that. And so before you add the sodium hydroxide, make sure the filter is safe. The way over here.
After.
Yeah. The first wash. The first wash, I collect. The second and third wash for silver chloride goes into waste. Leave the waste beaker there and then add sodium hydroxide.
That's for all of them. Save the first wash.
Save the first wash and then discard second and third wash. Here, save the first wash and don't bother doing a second and third wash because if it's not totally clean, it's not going to screw anything up. Here, save the first wash. Don't bother with the second and third wash. Here, we would save the first wash, but we're not going to use it for anything anyway. And so we would normally save the first wash, second and third wash discard, but we're discarding all the washes. We're going to do a second and third wash here. Why?
Because we're using it for another experiment.
Yeah, we're going to do another step to this, and we want this as pure as possible. Because we don't want any contamination here. The contamination leads to weird results here that we call interfering reactions, or interfering ions. It screws up the color, and other things happen. And so here we need to make sure it's clean for the subsequent steps. Okay, so you kind of got the feel for what we're doing?
So for the ammonium test, when you say that it's separate, the ammonium ion isn't necessarily separated from the
No.
ion, right?
It's a separate test, but it's all part of the same mixture. So the ammonium is part of this mixture. This is for the known. The known has everything. Your unknown is not going to have everything. let's say your unknown had ammonium and silver. And what that means is if you only have the ammonium and silver, what we're going to get is we're going to get this dark brown precipitate. But you can't tell, if there's no evidence of white precipitate, it's hard to tell. This dark brown, black, it all looks the same. However, if you had ammonium and lead, then you can tell. Because if you had ammonium and lead and no silver, no barium, no manganese, what you're going to get is white precipitate here. And so these interfering, even though these interfering things are happening, and they can mix you up, they can also give you some information. Not always, but we can use that. And so that's that. For the anion, you're going to get, the anion solution I think is on the bench top. So you're going to use 3 milliliters, about 3 squirts for each of the anion tests. I'll talk more about the reactions next time. Let's see, how many days are we doing this lab over? Does somebody have the syllabus?
At least 3, I think 3.
Yeah. 3 days?
Yeah.
It's a 3-part lab.
Do we have that many classes left? I think we have 4 labs left. Yeah, 4 labs left. So this one, what you want to do is you want to get through the known solution. The known solution, you can work with a partner, but you have to make sure that you and your partner see all the observations, because the unknown you're going to do individually. And so let's say you split up the work and you saw half the results, your partner saw the other half of the results. It's going to make it difficult when you come to your unknown, because you aren't going to know necessarily what to look for.
So we can work with a partner.
On the unknown, you can't, but for the known, you can. Everybody's going to get their own unknown, individual unknown.
Are we doing both tomorrow?
No. What you're going to do is you're going to run through the knowns, all of them, and it's probably going to take you at least 2 days. The unknown goes much faster. And so probably by the second day, some people will start their unknown. Depends on how smoothly things went. Some people will start their unknown on by the 3rd lab period.
I was actually talking to a Chem student, and he said something like he had to wait for his experiment to dry, and it was going to take a few days or something. That happens.
Yeah. That's why we have special drying ovens to dry things quickly. We have something called a vacuum drying oven, which dries.
So we should expect to have this whole flow chart and these two ammonium test and anion test done tomorrow?
No. Just have the first, you can kind of get a feel about how far you can make it. Just have that much done.
But what if we only get through like half of this? Is that okay?
That's fine. Yeah, some people will only get through half of it, more or less.
Seen anyone get through the whole thing?
No.
No.
No one's made it through the whole thing in one lab period. Maybe, the second or the third time you do it, you can make it through the whole thing.
I forget to call in will be the first.
The unknown, though, goes fast. But you want to do more than one unknown. The more unknown solutions you do, the more potential bonus points you can get. Yeah. Vapor equilibrium. So this is section 15.4, liquid vapor. What is the meaning of equilibrium? Yeah, equilibrium means stability, no change. Why do we describe a liquid vapor equilibrium as a dynamic equilibrium? So dynamic is change, but equilibrium is no change. And so what does dynamic equilibrium refer to here? Because it's changing, but no change.
There's change, but it equals out. So it's vaporizing, but it's also condensing at the same time.
Exactly. That's what it means. The dynamic part is the molecules never stop evaporating and condensing. It's just that there's no net change in how much vapor we have and how much liquid we have. And so we've reached a state of dynamic equilibrium. Explain why the rate of evaporation from a liquid depends on temperature.
Higher temperature means higher kinetic energy, and so if the particles are moving more, they're more likely to
Yeah.
use them.
Right. Higher temperature means higher kinetic energy, and if they're moving faster, then they can break free more easily, right? And then, or you can answer this in terms of the Maxwell-Boltzmann distribution. Higher temperature means what in terms of the population? We look at the Maxwell-Boltzmann distribution. The higher temperature means a greater population of higher energy particles, and there's going to be some cutoff here. That cutoff is going to be the minimum amount of energy required for vaporization. So the stronger the intermolecular force is, the further right. The weaker the intermolecular force is, the further left. So we can see that here in the figure. So I'll go back to the figure in a minute. So let's take a look at 48. Use the following vapor pressure data to answer the questions. In which liquid are the intermolecular attractive forces the strongest? A or B? Well, if you look at it, the vapor pressure is the same, but there are different temperatures. It's not fair. Which one is going to have a higher vapor pressure, you think? So let's say I raise this one up to 78. If I raise this one up to 78, what's going to happen to the vapor pressure?
Goes down.
If I increase the temperature, it goes up, yeah. It goes up because I'm going to vaporize more. So this one's going to have a higher vapor pressure. This one's going to have a lower vapor pressure. In other words, in order to hit 400, this one required a much higher temperature than this one here. And so since this one has a lower vapor pressure, it means it's less volatile, which means it's harder to vaporize, which means it has stronger intermolecular attraction. So C7H16, which would be heptane, has stronger attraction. And you have to note something. This one's polar. This is what we call an ester. This one's non-polar. And so what it's saying is that the London forces here in heptane are stronger than the dipole forces and the London forces here this is methyl ethanoate. And so sometimes it's hard to compare, because for big molecules, the London forces can be quite significant.
Esters are oil-based?
Yeah, like fats are esters.
I know, like
Fats are esters of this. Glycerol.
I know, like polyester is.
Oh yeah, the polyester is different though than ester. Change okay. All right, let's take a look at the boiling process here. Well, here's the cutoff. This is what I was talking about. This is the Maxwell-Boltzmann. And so temperature is going to shift this right or shift this left, and intermolecular attractions will shift this. The stronger the forces, the more right this cutoff is. The weaker the forces, the more left that cutoff is. And that's going to change the population, the shaded area there. Here's our dynamic equilibrium. Evaporation and condensation never stop. It's just that there's no change here. Let's reduce that point. Here are some vapor pressures. Which of these is most volatile? And so this is the temperature and the vapor pressure. Which of these three is the most volatile? The one with the highest vapor pressure. Which one has the highest vapor pressure? Diethyl ether? Yeah. Diethyl ether has the highest. Let's say we're at 0 degrees C. The vapor pressure of water is rock bottom. The vapor pressure of ethanol is right here. But the vapor pressure of diethyl ether is way up here. So diethyl ether has a much higher vapor pressure. If we go to 20 degrees C, water is still flatlining down here at the bottom, but ethanol has some vapor pressure. But diethyl ether has significant vapor pressure here. And so all these are at the same temperature. And so when we look at this chart back here, what that means is diethyl ether has a cutoff here. And so all this population can vaporize. Water has a cutoff here. And then, actually ethanol. Let's say ethanol has a cutoff here and water would have a cutoff here. Having stronger forces. When the vapor pressure hits 760 millimeters of mercury, then the vapor pressure is equal to normal atmospheric pressure. Normal atmospheric pressure is 760. And so if the vapor pressure of the liquid is the same as normal atmospheric pressure, then the temperature at which that hits is called the normal boiling point. And this is where the vapor pressure and atmospheric pressure match. So the normal boiling point of diethyl ether is really low, 34.6 degrees. Ethanol is less volatile, and its normal boiling point is a little higher, 78.3, and water is all the way up to 100. So this depends on vapor pressure. We can have just the regular boiling point. The regular boiling point, let's say on Everest, Everest is about a third of an atmosphere. And so water on Everest would boil at like 75 degrees C. So if you try to cook pasta at 75 degrees C, it's going to take you a long time. So you have to adjust the cooking time. Okay. Here's the impact of temperature. Which one's hotter? T1 or T2? Which one's hotter? T2. T2 is going to have a greater population of higher energy. So T2 is hotter, T1 is colder. Temperature. This is for the same liquid because the vaporization cutoff, E here, is the same for both. Okay, so we talked about boiling. Boiling is when the vapor pressure is equal to the atmospheric pressure. Then we have boiling occur. Boiling is when the liquid spontaneously converts to a gas. What we say is that the liquid and the gas are equilibrium or are in equilibrium with one another. Water is an unusual compound. They're looking for water on the moon. They're looking for water on Mars. You heard that?
Yeah.
Yeah.
Yeah, there is one.
They found.
Yeah, they found some. They found water on the moon. They found water on
There's a lot.
Mars. Yeah. Well, that's important because water is important for life. So, biochemist, if you're taking biochemistry, this would be one chapter: water, an unusual compound. When they talk about water, it has certain properties that are critical for life. And this is why they look for water on planets to see if there could be life on other planets.
They don't.
Global warming.
What's that?
Global warming Mars. It's more.
Global warm Mars? Oh, that's interesting.
There's like, so yeah, they wanted to reform like, there's like two different ways. They could like, try to like make it a greenhouse gas like environment.
Yeah.
So that everything happens. Or they want to use like a sun. Yeah.
I said ammonols. Ammonols. Did it wrong? Yeah. Warrior.
Yeah, or everything would have like radiation and stuff.
Warrior. How is it
That's
warrior?
what, I mean,
Warrior. When you say it too many words,
they're really into it. Like, Elon is really bored.
Yeah.
And like,
war?
it's super cool, of course. You can only go once every
Warrior. That's the word.
Get the slingshot there. Yeah.
Warrior.
I think it's atmosphere.
It depends. Like, it just is that sometimes.
Oh, is it?
Something like that.
I'm
Yeah, this.
praying. No, I'm heard that. This one's easy. I'm
So
beta.
going back to water, you know how it's
Yeah.
freezes
That's like
from
caramel.
the top
Like sometimes it's like
to the
caramel
bottom.
apple. Like I've never
Is
said
that because
caramel.
it's
This is the one that
It's because of
caramel
the
apple argues with me.
Ice is less dense than water.
No. Who argued against these?
Ice is less.
No.
That's one of the big things.
If I say it fast,
I
it's
tried
like,
walking on
no. But like if you say it slow, like
when I
no.
heard it crack.
No.
Yeah.
Like if you say it fast. No. No.
No, I know, but he keeps.
It's the day you die.
So going back to dry ice,
Say milk. Say milk.
it's basically carbon dioxide.
Yeah, solid carbon dioxide.
Turning into a gas. It will no longer be a solid.
Does it have similar properties to like liquid nitrogen?
Literally no one's.
Some, yeah. CO2 is very cold, and so it's used as a cryogenic material. And liquid nitrogen is very cold. It's used as a cryogenic material. So I used to use both in lab. CO2 is about CO2 is a little warmer than liquid nitrogen, so it depends on how cold you need to get. But CO2 is cheap and it's easy to work with. But the problem is CO2 dry ice does not have good thermal conductivity. And so what we did was we used dry ice and acetone. Acetone is very low, and so it's hard to freeze acetone. If you use dry ice and water, the water will freeze. And so we use dry ice and acetone and cool things down using that, and then it cools rapidly. Because liquids have much greater thermal conductivity than gases. Gases have poor thermal conductivity because gases have a lot of empty space, except for one gas. Do you know a gas that has thermal conductivity greater than water? This is really weird. You know, the special properties of water, do you know the special properties of water for life? One, solid, water, ice is less dense than liquid. This is the opposite of most things. And so ice floats. 2, water has high, what they call specific heat. Water can absorb a lot of energy without changing its temperature. So when you're boiling a pot of water, it takes so long to boil, doesn't it? 5 minutes. People use IH heaters. Have you seen IH heaters? IH heaters, that boils water much more rapidly, like a minute rather than 5 to 10 minutes. I timed it. To boil my pot of water for pasta takes me 10 minutes, plus the pasta another 14 minutes, so 24 minutes altogether. But
What is inconvenience?
You put salt in there, it boils faster.
salt, there are different reasons. People say the salt is going to increase the temperature. So if it increases the temperature, the pasta will boil faster. Because the hotter the temperature, the faster things cook. Right? And so, but the amount of salt, because people put a pinch of salt in there, a pinch of salt will only increase the temperature of the boiling point by like 0.1 degrees, something like that. So if it only increases by 0.1 degrees, is that really going to make things cook faster? No. And so other people say they put salt to make it taste better, but it really doesn't increase the speed. And so it has that, and it has good thermal conductivity. So if you try to cool, like I was watching this cooking show, and it's time, so they only have 1 hour, and they have warm beer. And the professional chef there said, I wonder if this guy knows how to cool beer fast, And then there's a secret. So I was really interested in what is the secret for cooling beer fast, And then I found out. Well, then I thought, oh, that's so obvious. You know how not ice water. Cool the beer in ice water, and then there's much better. Versus if you put it in ice, like a bucket of ice, it takes a long time because there's poor thermal conductivity between ice and the beer can. But if it's in ice water, then you have excellent thermal conductivity. Yeah, or ice water. Yeah, if you put salt in there, then you can get the temperature even colder. And so that's another good idea, salt, like making ice cream. We'll talk about that in the next chapter. But, I saw something very interesting. Have you heard of these HT nuclear reactors? HT nuclear reactors. Anyway, something's got to be done to make electricity less expensive. Because I think electricity prices, when I took Tesla to Santa Barbara, it used to be under $10 to charge it. And then went this last weekend, it was like $17.50 to charge it. And then I calculated the miles, and then calculated how. This is a Tesla supercharger. Superchargers are like 53 cents per kilowatt hour, so it's kind of expensive. But home is still 43 cents. It's not that much cheaper. But it was about the same price as driving a Camry, too. With the current gas prices. So I was thinking, wow, it's not much of a savings. As far as, because there's a lot of hype about how much cheaper it is, electricity versus. And so I calculate, if you get like 34 miles per gallon, then gas would cost the same at the current gas price. But anyway, if you can make electricity cheaper, that would be good. But the problem is electricity probably is going to get more expensive as demand increases. Then they'll just keep increasing the price of electricity. But some promising things for electricity, these new nuclear reactors. These new nuclear reactors, this is technology that's being developed in Japan. Japan has cut nuclear power after what happened at Fukushima, which is a huge disaster. But I guess they have safer reactors there. But one of these reactors is the HG, high temperature reactor. And rather than using liquids to cool it, do you know what they use? They use a gas to cool it. And gas is totally counterintuitive because you think, how cooling using gas is like air-cooled, like those old air-cooled Volkswagens versus the water-cooled ones. The water-cooled ones run much cooler in temperature. Air-cooled ones are not very efficient. But it turns out that helium is even better than water. Water is an excellent coolant. During Fukushima, I remember Clinton had mentioned that there's some super, top secret coolant that they could use to prevent nuclear meltdown. They need to quench the heat before things start to melt in the nuclear reactor. And then at the time, the politicians in Japan said, no, we got it handled. But, at that time, it had already melted down. That's what they meant. They don't need it because the reactor already melted down. But if it hadn't melted down, then they should have given, this is the coolant that they use in nuclear powered subs. So, it's something that will quench the heat. Water is an excellent, quencher of heat, but there's better stuff out there. I wonder, and it makes me wonder, what is that top secret material? I want to know what that is. I probably can figure it out, looking at it, but it's kind of got me thinking about that. But, one thing that totally surprised me is helium. You wouldn't think helium is excellent at quenching heat, but helium gas is. Helium gas has a specific heat that's greater than water. Water's specific heat is 4 joules. I think helium is like 5. It's higher. And it has excellent thermal conductivity, like gold. Gold has excellent thermal conductivity, but you wouldn't expect a gas. So maybe I'll show something about those reactors. But that's promising, and that might give a good way to make cheap electricity, which can result in, cheaper prices for charging the car, and also more environmental friendly because then they can produce things like hydrogen much
I'll
more.
revisit what Nikola Tesla was doing with the atmosphere.
Oh yeah,
There's another, they use thorium.
thorium reactor, yeah. But there's still a lot, there's people that say, oh, thorium's been around since the 50s, but it's never going to be practical. And then there are other people that say that it's going to be the next revolution.
Isn't it because the higher ups at that point when reactors will be being developed in the 1950s, 1960s, they put all the resources and the money into the conventional reactor.
Yeah.
Thorium, supposedly the molten salt reactors are much better.
Yeah.
They're much less prone to big environmental meltdowns.
Yeah.
They have passive.
It's good out.
Yeah.
They need plutonium starting radiating energies. So the design is once you have a functional meltdown, you just separate the plutonium and water from the thorium reactor and it starts naturally cleaning up outside.
Yeah, that's interesting. Well, anyway, we're out of time, so.
Yeah.
Talk more.
I don't like that. I'm not a